Molecular geometry basically explains the arrangements of atoms in a molecule in 3 dimensions. So it's how they're spatially arranged. So it's the 3-dimensional arrangement of atoms within a molecule. So we're talking about covalent molecules. Shape is important for physical and chemical properties of compounds. Physical being melting point, boiling point, densities, states. In terms of chemical properties, how it reacts. In biological molecules, we have things called enzymes, and their function depends on their shape. The lock and key mechanism for enzymes and substrates, very dependent on shape. So the physical, boiling point, melting point, etc. The first step to getting a good molecular shape, a fairly accurate shape, is if we have a decent Lewis structure. So the correct Lewis structures are crucial to determining the shape. So do not take shortcuts when you're doing your Lewis structures. Another key component to shape is the fact that valence shell electrons repel each other. They want to be far apart from each other as they possibly can. So of course our valence shell electrons are those that are involved in that outermost orbit, and we have 2 types of valence shell electrons. We've got lone pairs, and we have bonding pairs. So these will orientate themselves in a way that they are maximum distance apart in a 3-dimensional model. We're going to look at one bonding theory, and that's VSEPR. This is valence shell electron pair repulsion. So our bonding and our lone pairs in our valence shell are going to repel each other. Now, lone electron pairs take up more room, more space than bonding pairs. So when we have a structure that has 8 electrons around the central atom, if there are 4 bonds, they will have a different shape than a central atom that has 3 bonds and 1 lone pair. So we're going to see some distortion as we add lone pairs of electrons. So before we get started, a couple of things you need to know about our structures that we're going to draw. A is going to represent our central atom. So usually this is the one with the highest combining capacity. X is going to represent atoms bonded to the central atom. and E is going to represent pairs of lone electrons on the central atom. So it's pretty much all about the central atom. The A atom is what we're going to be looking at for the shape. We also have to look at how we're going to draw the bonds too. So we've been drawing bonds like this, a straight, solid line. So this is going to be for bonds in the plane of the paper. A dashed line is going to be a bond that extends behind the paper, and a wedge is going to represent a bond coming out of your paper. So we're going to have a solid line, a dashed line, and a wedge. Okay, so we're going to get started. So our very first example, AX2, so this is telling us we've got the central atom A, and it's bonded to two atoms, X. There are no lone pairs of electrons because there's no E in the general formula. So we've got two bonding pairs, one pair for each X, 0 lone electron pairs because there's no E in the formula. So if we add those two together, we have got 2 pairs of electrons. So now we've got electron pair geometry and molecular geometry. So electron pair geometry includes lone pairs. Molecular geometry does not show them, but because we know that they're there, if you have an E in your general formula, we know they take up space. So I'm going to show you where they are for electron pair geometry, but this is what I'm expecting from you. I'm not going to want you to draw these electron pair geometry. I just want the molecular. So, in a case where we don't have any lone pairs of electrons, our geometries will be the same. So I've got A bonded to an X, bonded to an X. So because there's only 2 bonding pairs, they are far away from each other when they're 180 degrees apart. So this is considered to be linear, because X to A to X makes a straight line. So our molecular geometry will be the same. It's linear. An example of this is the carbon dioxide molecule. Okay, next we're going to look at AX3. There's 3 atoms bonded to our central atom, so we've got 3 bonding pairs. There's no E in the formula, so we have 0 lone pairs of electrons, so for a total of 3. So our molecular and our electron pair geometry is going to be the same. This time, the electrons are going to be as far apart as possible, and if you have 3, you make a triangle. So these are 120 degrees from each other. So these geometries are the same. And if you connected the X's, you would form a triangle. So these are called trigonal, planar, or trig-planar. So these are trigonal, planar because they are actually in the plane of your page. They are flat. And a good example of this is any binary compound with boron, like BF3. Next example I'll do is AX2E, and then I'm going to go back to just doing the ones with no lone electron pairs. So this one, we've got a central atom, it's got 2 atoms bonded to it and a lone pair. So it's got 2 bonding pairs, 1 lone pair for a total of 3. So its electron pair geometry will be the same as this one because I've got 3 total. So now I'm going to show my lone pair. So this would be trig planar. However, for our molecular geometry, we only show the x's. You'll notice you keep the same shape where your x's are. So this no longer forms a triangle like this one did. Instead, it forms a V or a bent shape. So this is either V-shaped or bent. Normally we call it bent. An example of this is sulfur dioxide. Okay, AX4. So we have 4x atoms. So we've got 4 bonding pairs, no lone pairs of electrons for a total of 4. So now this one gets a little trickier. We have 2 bonds in the same plane as the paper. One sticks out but goes down, and then one sticks to the back and goes down for X. So the molecular geometry is exactly the same. 2 are in the plane, one goes up, one goes down, then you've got one coming down to the right and one going to the back but down to the right. So the angles here are 109.5 degrees, and this is considered to be tetrahedral because we make a 4-sided figure. And an example of this is methane. Okay, turn over the page and we're going to do AX5. So we've got 5 bonding pairs, no lone pairs for a total of 5. So now we have a central atom. We're going to have 2 X atoms along this axis, and then we're going to have the other 3 in like an equatorial plane. So one is going to be in the same plane as the other 2. One's going to come out, and one is going to go back behind the paper. So you're going to form a triangle in the middle, and then it also connects to the top and the bottom. Our molecular geometry is exactly the same. So we can just draw it like this. Now the name of this one is called Trigonal because the equatorial part in the middle here forms a triangle. So this is Trigonal and it goes above and below that plane, so it's bipyramidal. Trigonal, bipyramidal. And an example of this is antimony pentachloride. The bond angle for this one is, in this axis, these are 180 degrees from each other. In the equatorial plane, these are 120 degrees from each other. And then it's 90 degrees between the axis here, the vertical axis, and the equatorial plane. Now move further down the page to AX6. So now we've got 6 bonding electrons, no lone pairs, for a total of 6. Now we're going to have all of the atoms within 90 degrees of other atoms. So what we have here is 2 coming out of the plane towards us, 2 going back, and 2 in the plane up and down. So these are, any x is 90 degrees from another x. Our molecular geometry is exactly the same. We call this octahedral because we will be making 4 triangles on the top and 4 triangles on the bottom. So 8 sides, 8 faces. So this is called octahedral. And an example of this is sulfur hexafluoride. So that shows the electron pair geometry and molecular geometry for those structures that have no lone pairs. The next video will show you how to fill in the rest of the table when we have lone pairs of electrons, also on the central atom.